I want to talk a little bit more about some of the things that we can get out of the sum and difference identities that we talked about during the last lecture. Because there's a few different applications that you can, like new identities that you can pull out of this that aren't necessarily obvious from the start. Now, the first thing that I want to observe is that from the identities that we had for sine and cosine, which hopefully you guys have in your notes, we can actually work out the sum and difference identities involved for other trig functions as well. So, for example, tangent. Although in a lot of cases, it's probably just as easy to say, hey, look, let's just rewrite everything in terms of sines and cosines, use the sine and cosine identity, and be done with it. But for some applications, you're going to probably be interested in using the identities for other things. So if I wanted to, for example, find the tangent of, let's say, alpha plus beta, so two angles alpha and beta. Well, the way that I can do this is I can remember that this is the sine of alpha plus beta divided by the, why am I writing sine? Divided by the cosine of alpha plus beta. That's just the definition of the tangent that I'm using there. And now what I can do is I can go back to what we said last time, and I can rewrite sine of alpha plus beta using the sum identity for sine. I can rewrite cosine alpha plus beta using the sum identity for cosine. And if I do that, I'm going to get the sine alpha cos beta plus cos alpha sine beta, and then all of that is going to be divided by cosine alpha cosine beta minus sine alpha sine beta. Now, this is itself kind of a mess, but it turns out that we can, in fact, rewrite this somewhat into a nicer form if we wanted to. And the way that we have to do this is we would need to go ahead and do a bunch of simplification on here. Now, we've seen this kind of simplification before, so I don't think it's really necessary to go through the whole thing again. I will just tell you what this comes out to be is going to be tangent alpha plus tangent beta divided by 1 minus tangent alpha tangent beta. And to prove that these two things are equal, well, you can verify this identity by using the methods that we used in the last section. So you could rewrite this in terms of sines and cosines and get it out. You could try messing around with this part, but it turns out that this is what you get when you simplify it down. It's nothing we haven't really done before, so I will leave it to you guys to work that out. And if you try working it out, you can't figure it out, and you really want to know how it's done, then let me know and I can show you how to do it. But I'm not going to bother doing it here for now. And we could work out similar things for cotangent, for cosecant, for secant, but it turns out that for various reasons, generally speaking, you can turn any question you have about those into a sine and cosine. I mean, that's always the case. And essentially, most people only really care about the sine and cosine identities because it turns out that for most applications, you only really need the sine and cosine stuff. For example, in calculus, all you really need are the sine and cosine identities in calculus, and then you can get everything else from general principles based on how these things are defined in terms of sine and cosine. But you can work out these kinds of identities for cosecant, for secant, and so on. Cotangent as well. That was for tangent, but you can also work this out for cotangent. Another thing that we can do if we wanted to is, and I'm sorry, I do keep having to refer to notes here, because some of these things are identities that are kind of obscure that people don't really use a lot anymore. So another thing that we could do if we wanted to is we could work out what are called the product identities. And I want to just show you an example of getting one of these product identities. So the idea behind getting this product identity is, let's suppose that I want to know what is cosine alpha times cosine beta. Here's the idea that I'm going to use to work this out. Okay, so I'm going to go back and I'm going to take a look at the list of the sum and difference identities. And I see that cosine alpha, cosine beta happens to show up in two of them. I have that the cosine of alpha plus beta is equal to cosine alpha, cosine beta minus sine alpha, sine beta. And then it also shows up in cosine alpha minus beta, because that is equal to cosine alpha cosine beta plus sine alpha sine beta. Well, how does this help me? Why would I look at these things? The reason that I want to look at these things is because I can notice now, and this is the observation that made people probably think about this in the first place, notice that in these two equations, in these two identities, the second terms are the same except that they have opposite signs. Up here, this is being subtracted. Here, it's being added. This sine alpha, sine beta. Well, that means, think back to what you did in algebra when you were solving equations. One thing we know from solving equation methods is you can add two equations together and get another true equation. So you add the left-hand sides of the equations and you add the right-hand sides of the equations and you get another true equation. So let's see what happens if I do that with these two equations. If I add these together, on the left-hand side, I get cosine alpha plus beta plus cosine of alpha minus beta. And then on the right-hand side, well, these two are the same thing. So I just get a pair of those. So 2 cos alpha cos beta. And then these two terms are the same, except one is negative, one is positive. So these two terms cancel each other out, and I don't get anything. I just get 0 for that last term. And now, if I divide both sides by 2, I see that cosine alpha times cosine beta is equal to cosine alpha plus beta plus cosine alpha minus beta, all divided by 2. It's a neat little trick to get this identity. Now, this identity is not one that people use a tremendous amount anymore for various reasons, but one of the things that this used to be used for sometimes was actually for figuring out products without having to take products. So basically, you would do this sort of like the way that you could do products using logarithms. In essence, you would take your two numbers, you would find two angles such that the cosine of the first angle and the cosine of the second angle are actually the two numbers you want to multiply. And then you could just add the angles and take the difference of the angles, look up the cosines of those, and work out this formula. And hey, that's actually the product of your original two numbers that you wanted to deal with. Now, that's kind of similar to the way that you could do products using log tables, which is one of the methods that people used to multiply complicated numbers back before everybody had access to a pocket calculator, or now a calculator on your cell phone, or whatever you happen to have with you. This is not super surprising, because remember that actually, if you watched the little bonus extra lecture that I gave last week, Euler's identity says that there's a close relationship between exponentials and trig functions. So yeah, there's no, like, in some sense, it's kind of doing the same idea as what you would do when you would look things up in log tables to do multiplication. Now, in addition to finding cosine alpha times cosine beta with this method, you can actually find a couple more identities by using the same kinds of reasoning. And since it's almost exactly the same kind of reasoning, I'm just going to write down the upshot of what you get rather than showing you guys the same thing 3 times in a row. So what you find is that the sine of alpha times the cosine of beta is equal to sine alpha plus beta plus sine alpha minus beta, all divided by 2. You find that the sine alpha times the sine of beta is equal to cosine of alpha minus beta plus, these are really obscure. They're not things that I work with a great deal. So cosine alpha minus beta minus cosine alpha plus beta, all divided by 2. And then, of course, we have the cosine times cosine identity, which I had down here but just erased. So these are a couple of additional identities that we can get by using the sum and the difference identities that we have. By the way, I should tell you that in some sources, the sum and difference identities, these are actually called Ptolemy's identities. So Ptolemy was a Greek mathematician and astronomer who lived over 2,000 years ago, I believe, like 2,200 years ago. I don't remember exactly when he lived, but a long time ago. Ancient Greek guy. He came up with a very accurate way of predicting astronomical observations. He basically came up with a way of predicting where you would see the various planets at any given time. But in addition to that, I'm not sure if he actually developed the sum and difference identities, but in any case, they're kind of named after him. So if you see somebody talking about Ptolemy's identities, the P is kind of silent in this Greek word, Greek name. If you see someone talking about Ptolemy's identities, that's what they are talking about. All right. So this has been a somewhat shorter lecture, but I am going to stop this one here and just encourage you guys to keep on practicing with these identities, using them to work things out, and let me know if you guys end up with any questions. In the next lecture, we're going to start talking about getting double angle and half angle identities, which are also super useful for us.